Today we're learning about implicit differentiation. So far, all the functions we've taken derivatives of have been written explicitly as a function of x, that y is equal to a function of x. However, I could have something where it is implied that y is a function of x. For instance, if I had the relationship x times y equals 1, I don't have y on one side and only x is on the other, but all I have to do is divide both sides by x, and then I could have it explicitly as y is a function of x. So for something like x times y equals 1, that's exactly what I would do. I would solve for y. I can get 1 over x. I realized to take the derivative of that, I would need to rewrite it to use the power rule as x to the negative 1, and then I would use the power rule and I could get the answer. The issue is that sometimes we literally are not able to. We either don't have the algebra skills, or it's just not possible to get a single y by itself on one side. So here's an example of a function like that, where you have multiple y's, one's being squared, so you'd have to square root it, but then you still have the other y. If you think for a minute about trying to get y by itself on one side in this, you'll realize that it's very difficult or impossible. So in that case, we need to actually leave it exactly how it is and take the derivative. And we don't know y equals, something with just x's in it, but it is some function of x. We just don't know what it is. So that is going to be called implicit differentiation. We're going to leave the function how it is, but we're just going to keep in mind that y is some function of x. So anytime we take a derivative of x, we do it like usual. Anytime we take the derivative of y, we have to remember that y is some function of x, and whenever we have an inside and outside function, we need a chain rule. So we will need to multiply by that derivative of the inside function y, which would be dy dx. So, for example, if I'm taking the derivative with respect to x of x cubed, the variables match. It's no different than what we've been doing in previous sections. The answer is 3x squared. Over here, though, if I'm taking the derivative with respect to x of y cubed, the variables do not match. Y is some function of x, but I don't know what function of x. Now, I don't get just to make up a function of x, but I just want to show you an example. So let's pretend that y is x squared plus 5x. Then when you're being asked to take the derivative of y cubed, it'd be like you being asked to take the derivative of x squared plus 5x cubed. And if you did that, you would need the chain rule. There's an outside function, power function. You would bring down the power, leave the inside alone, subtract 1 from the power, and then multiply by the derivative of the inside. Well, remember, I was just making up an example function, giving y some function of x to help you wrap your head around it. But if I put it back in terms of y's, there's my 3. I left the inside alone, that's y. I subtracted 1 from my power, that's squared. And then I multiplied by the derivative of the inside y function, which is dy dx. So the answer to this is 3y squared dy dx. Again, I don't know what function of x y is, but it is some function of x, so I have to treat it as such. So I'll take the derivative like normal, but then multiply by dy dx. In part C, you'll see we have a combination. We have one term that's just x's, so we take its derivative like normal. The derivative of x is 1. And then the other term has a y in it. So we take its derivative like normal. The derivative of 3y is 3, because the derivative of y will be 1. But then because of the chain rule, and y is some function of x, then we have to multiply by the derivative of the inside, dy dx. One more thing to watch out for is here I have the derivative of x times y squared. Well, both x and y are some function of x. That means I'm multiplying two functions of x together, which means that I need the product rule. That is, the first times I'm going to take the derivative of the second, plus the second times I'm going to take the derivative of the first. And then I go back and I do that. When I do the derivative of y squared, I do it like normal, 2y to the first, but I have to remember the chain rule, times dy dx. But now when I go do this little baby derivative, its variables match. So I just do it like normal. The derivative of x is 1. And then you can rearrange things a little bit, but you were already done at the previous step. So those are kind of just warm-up examples, because what a real problem will look like is an equation. So here's the steps for finding a derivative implicitly. You're going to have an equation. You're going to take the derivative of both sides with respect to x. In doing so, you're going to get some dy dx's, because basically what this boils down to is whenever you take the derivative of something with a y in it, you need to remember to multiply by dy dx. What you're really doing there is the chain rule, but what it boils down to is that you're just multiplying by dy dx. And then you're going to have some terms with dy dx's in them and some terms without. So you're going to get all the dy dx's on one side and everything without it on the other. And then you're going to factor out the dy dx and divide both sides by that to get dy dx by itself. So let me show you what that looks like in an example. We're going to take the derivative of both sides of the equation, every single term, remembering that whenever we take the derivative of y, we need to multiply by dy dx, but it's otherwise done normally. Derivative of y cubed is 3y squared, dy dx, plus derivative of y squared is 2y times dy dx, minus derivative of 5y is 5 times dy dx. Then this last one, the derivative of x squared is just 2x because the variables matched. The derivative of the constant negative 4 is 0. Now notice that you have three terms that have dy dx in them. I want to keep all of them together on one side and move anything without dy dx on it to the other side. So I added 2x to the other side. Now everything on the left side has a dy dx in it. That is a factor that they have in common that I can bring out in front. So if I bring dy dx out in front, I've factored it, and then I have 3y squared plus 2y minus 5. And now to get dy dx completely by itself, I can divide both sides by 3y squared plus 2y minus 5, and I get this fraction. So you do expect to get this fractional look to many of these problems. Most of these implicit differentiation problems are going to end up being fractions because of this factoring out of dy dx and dividing. And it is okay for it to have both x's and y's in it. It won't always, so don't think that we're tricking you if it doesn't, but it often will have both dy dx, both x and y in it. So even though these are not functions, because it doesn't pass the vertical line test, it is a relationship, and the derivative does still show you the slope of the tangent line. So just to give you an example, I picked a couple nice points, like the point 2, 0. What I'm going to do is replace all x's in this derivative formula with 2 and all y's in this derivative formula with 0. And what I get is negative 4/5. So while you may not be able to measure this exactly, you can see that it seems reasonable that that slope is close to negative 1 or about negative 4/5. As another nice spot here at 1, 1, you can see I end up with a vertical tangent line if I draw it. If I replace all x's and y's with 1's, then I get 2 divided by 0, which is undefined. Undefined slope means I have a vertical tangent line. So you can confirm for yourself that you do get those tangent lines when you're taking derivatives this way as well. So let's look at another example. And we just want to kind of see what happens with some more difficult things where we end up with chain rule and product rule and that sort of thing. So process is going to be the same. I take the derivative of both sides with respect to x, but I need some of my different derivative rules. So here you can see that I need the chain rule. And I need the chain rule regardless of the fact that there's x's and y's. I have an inside and outside function. So the derivative here, I would bring down the power and multiply it by what's already there to get 6. I would leave the inside alone and subtract 1 from the power, so now there's a hidden 1 power here. And then the chain rule says I would need to take the derivative of the inside. Well, the derivative of x squared plus y squared would be 2x plus 2y, but remember, whenever I take the derivative of y, I have to multiply by dy dx. On the right-hand side, I need the product rule because both x and y are functions of x. So I'm treating 100x as my first and y as my second. So I have first times the derivative of y is dy dx, plus the second times the derivative of 100x is 100. After this, I do have to be careful. It's really more the algebra that I'm worried about here than the calculus for you. In order to get all my dy dx's together, I first have to get them each to be kind of freestanding terms. So I have this whole chunk, 6 times x squared plus y squared, that's being distributed to the 2x plus 2y dy dx. So I actually need to distribute that whole chunk to each one. so that this dy dx term, the 12y x squared plus y squared dy dx, is by itself and is allowed to move around and get grouped with the other dy dx term. So I distributed that to each one, and you can see that here. And now I'm going to get all my dy dx terms on the left and subtract off anything that didn't have it and move it to the right. So this 12x times x squared plus y squared does not have a dy dx, so I subtracted it over to be with 100y, whereas this 100x dy dx had one, so I subtracted it over to be over here with the 12y x squared plus y squared dy dx. Now both things on the left have a dy dx in them that can be factored out, and then to get dy dx completely by itself, I divide both sides by this big crazy chunk, 12y times x squared plus y squared minus 100x. Again, you see that fractional look with a mixture of both x's and y's, and I can test a certain point. For instance, I think I was asked about the point 31. If I plug in, and I need to be really careful that I plug in 3's for x's and 1's for y's, not the other way around, I get 13/9, which is about 1.444, and you can see that that is a positive slope that looks like it is a little bit steeper than 1, so it does seem reasonable. We do not have to have the picture, but it's nice to confirm with. Here's another example that involves e's and trigs. So again, I'm taking the derivatives like I always would, but whenever I get to the derivative of y, I multiply by dy dx. On the left-hand side, I only have x's. The derivative of e is itself times the derivative of its exponent, because that is its inside, so that's 5e to 5x. On the right-hand side, however, I have the chain rule. The derivative of the outside function sine would be cosine. I leave the inside alone, and then I multiply by the derivative of the inside. Well, the derivative of the inside is going to need that implicit differentiation. The derivative of the x is 1, but the derivative of 8y is 8 times dy dx for that chain rule implicit differentiation. Similar to the problem we saw above, I need to distribute that whole chunk cosine to this parentheses with two things in it so that the dy dx term is free floating and can be isolated. So I need to distribute the cosine to the 1 and to the 8 dy dx, and you can see I have that here. Now I want to get everything that doesn't have a dy dx together on one side. Since the 5e to the 5x already didn't have it, then the easiest thing to do was just to subtract the cosine of 8x plus 8y over. And now the right-hand side is the one that has dy dx. And I just reordered it to help you see that then to get dy dx completely by itself, I just need to divide both sides by 8 cosine of x plus 8y. Again, pretty ugly looking fraction, but I'm not asking you to simplify or anything like that, so that is a fine final answer. Just type carefully in my math lab. Lastly, we can be asked to find a second derivative. So, of course, just like any other, we have to first find the first derivative. So we would find the first derivative implicitly, like we have been. Derivative of x squared is 2x, derivative of y squared is 2y times dy dx. The derivative of 25 is 0. Now I would get dy dx's together on one side and those that don't have it on the other, so I'm going to subtract 2x. Then to get dy dx completely by itself, I'll divide both sides by 2y. Now I know what the first derivative is. I could simplify, cancel those 2's, and I get negative x over y. So the first derivative is negative x over y. Well, if I go to take the second derivative, that's going to need the quotient rule. The quotient rule is the bottom times the derivative of the top, which would be negative 1, minus the top times the derivative of the bottom would be 1 times dy dx. The derivative of y is dy dx. All over the bottom squared, which is y squared. Now, we can't still have a dy dx in it. We want only x's and y's in our final answer. But remember that we found what dy dx was. We found that dy dx was negative x over y. So I can replace the first derivative that popped up in the middle of my equation, dy dx, with negative x over y. So I'm going to plop that in there. Now notice that I really am completely done. I only have x's and y's. I don't have dy dx's floating around in there too, so I do have to do this step to be completely done. Now there is some more simplifying you could do so that you don't have a fraction within a fraction, but I'm not going to make you do that. So this is a fine final answer for me. But you do absolutely have to go make that substitution from where you found what the first derivative was and plug it in here so that you only have x's and y's, not derivatives. That is kind of the trick with a question in an implicit differentiation problem where you're asked to find the second derivative. The first derivative will show up somewhere in it, and you need to replace what you already found. That is implicit differentiation. Go online and do your 3.7 homework to practice it in my math lab.